Okay, now I want to talk about this graph. This one shows even better about the stability of nucleus. Okay, this one will show about the stability of nucleus. Yeah, even better. Okay, so we know that stability of nucleus is proportional to binding energy per nucleon. Okay, the higher the, oh my god, the higher the binding energy, the higher the stability. However, the higher the nucleon number, the lower the stability of nucleus. Okay, now, so let's see about this one. You see from here, this one, this is the deuterium hydrogen atom. Okay, going up, you see why the binding energy per nucleon increasing sharply over here? Because we know that, you see, this is the x-axis is the mass number. So going to the right means the nucleus become bigger and bigger. Yeah, the nucleus become bigger and bigger. So I can say is this one is just small nucleus and then become bigger and bigger, more and more proton and neutron together. Understand? More and more proton. This one, maybe this one only have one proton, one neutron. Maybe this one got 82 proton here, and how many? I don't so sure. How many neutron are there? 156 neutron. See, so bigger and bigger nucleus. All right, and then which one more stable? This is the binding energy per nucleon. Okay, the y-axis is the binding energy per nucleon, which is E, the binding energy per nucleon. So the higher the graph, we know that the higher the graph, the higher the stability. So you see the graph is the highest over here. The graph is the highest at this mass, which is from 50 up to let me just use the red pen. Okay, so it is the binding energy per nucleon is the highest between 80 to 50. The mass number or nucleon number 50 to 80 has the highest okay, very high, I can say very high binding energy per nucleus. Binding energy per nucleon, very high, very high binding energy per nucleon, which is 8 to 8.9 mega electron volt per nucleon. So this part is very stable nucleus compared to the other part. Okay, for the most stable nucleus is the nickel. Okay, nickel, you know nickel? Nickel is the most stable one. It is at the nucleon number 62 over here. Yeah, 62. This is the one lah. This is the one. Nickel 62. Okay, most stable nucleus. Then the binding energy per nucleon is 8.7945 mega electron volt per nucleon. This is the most stable one. Okay, because it has the highest graph. Okay. But talking about this one, if the graph going further and further away to the right hand side, you can see the graph decreases. The graph decreases means the stability decreases. This one is more stable, but when the nucleus become bigger and bigger, they become less and less stable. Why become less and less stable? Because if we look at the equation itself, become less and less stable because why? Although we know the binding energy also increase, the bigger the nucleus, the more the mass defect, the higher the binding energy, However, the nucleon number also increases, but even at a faster rate. The binding energy increase, but the nucleon number increase even faster. You get what I mean? The binding energy increase, supposed to be going to a bigger nucleus, it become more and more stable because with higher binding energy. But as we know, when the mass number increases, going to the right, the mass number increases even faster, yeah, at an even faster rate compared to the binding energy. Increase even faster. So overall, as you go to the right, actually the binding energy per nucleon decreases steadily, decreases slowly, because we know that the binding energy become bigger and bigger. Although the binding energy become bigger and bigger, however, you must not neglect that as the nucleus become bigger and bigger, there'll be more protons. There'll be more protons now in the nucleus. As you see here, you have 82 protons here, 82 protons here repelling each other. I cannot finish drawing all the protons here. Protons, of course, there are also neutrons. Neutrons in between. I just couldn't finish drawing all the. If you have a big nucleus, means there are a lot of protons there repel each other. The experience for big nucleus like uranium, like the uranium-238, it experience very, very high repulsive Coulomb force. In the nucleus, due to lots of protons, and these protons very near to each other, have very, very small r distance between the charge. You see that? It has very, very high Coulomb force inside the nucleus due to lots of protons. So this one weaken the stability, lower the stability of the nucleus. That's why in the end, like when the nucleon number goes up to 200 and 240, it becomes unstable and radioactive nuclei. Unstable and radioactive nuclei means at any time they will disintegrate, they will decay to form a more stable nucleus. The element will tend to it will decay. This uranium will decay and go to this side. Go to the left hand side. The graph tend to go to the right hand side to form a more stable nucleus over here. Okay, so at here is very unstable already because the nucleus has become too big, too many protons in the nucleus, repelling each other in the nucleus, so become very unstable. As I said, as the graph go to the right hand side, although the binding energy increase, but the nucleon number increase even faster. So overall it decreases. So we can say the stability which is proportional to the binding energy per nucleon also decreases. Also decreases. So so that's it. So when the nucleus become very big, it become unstable and radioactive nuclei. Okay. So I think that's all for this this part. Okay. Later on, I will discuss about the problem. Some problem how to calculate the binding energy and binding energy per nucleon, and all the E equal to mc square. How to convert the unit between mega electron volt to joule, atomic mass unit to kilogram. I will talk in the problem solving part. All right. So this is the concept only. Okay. So next video I will talk about radioactivity. Okay. See you in the next video. Bye.